Okay, the plan for today is basically to finish up 5.3 and work through 5.4. 5.4 is not that big of a section, just a couple of ideas related to fundamental theorem of calculus and integrals. The quote of the day today is two quotes. Unfortunately, I'm not sure what the source is for either of these quotes. The first one is attributed to Gandhi, but I am not sure if that's true. And the second one is often attributed to Seneca, the Roman philosopher, the Roman Stoic philosopher, and but it seems to be that that's misattribution. So, but either way, I think that both quotes have merit. The first is something along the lines of the future depends on what you do today, or the future depends on what you do in the present. And the second, luck is what happens when preparation meets opportunity. So the kind of thought for today is looking forward to career. That's, why most people, take college courses is looking to get a degree and for that to lead into a career. Um, on one hand, with your career, uh, people will say, oh, it was so lucky or fortunate that this opportunity came around, but that opportunity is only valuable if you have the preparation to meet it. So if a great job opens up, but you know, you don't have the preparation, the background, whatever it may be to get that job, then you know that's not a lucky event, so to speak. Um, and in light of that, well, what does preparation look like? It looks like making choices today that impact the future. So, what can you do today? Maybe in your choices for your gen eds next semester or um, your why can't I think of the term for it? But the unrestricted courses that you can take next semester, what courses will you choose to take? Is it better to take maybe a programming course or maybe a course in some basic, accounting or business or something like that? What direction do you want to take your education in some of those electives? That was the word I was trying to think of. Um, you know, if you take an elective this direction versus that direction, that will prepare you in a different way for, future career prospects. Um, and some thoughts on this, probably one of the top, 4 or 5 best assignments that I've done throughout my whole college career when I was a student. It was actually part of an English class. It was my freshman year, and I was never English class never really was my favorite class or anything like that. Obviously, I liked the math and technical stuff a little bit more than the kind of English and arts kind of stuff. But in a course called Argument and Research, which we have a similar course that folks often take, um, we were tasked with looking at our career path, at our major, what we plan to do with our career as first year in college freshmen, and to research it, to go to Bureau of Labor Statistics government website and look at things like projected salary, projected demand for that degree or for that job in the future. Does it seem like demand's going to increase or decrease? Is it a career that they think is going to be in demand in the next 3, 5, 10 years? What do the salary expectations look like? Is the salary in line with what you kind of expect with what you can support a family with and so on, or is that salary not going to meet your expectations? So looking at more the objective side of things and also the subjective side of things. So looking more anecdotally, maybe find somebody who's actually doing the job, who's in the position that you see yourself in maybe 3 to 5 years into your career, and see if you can shadow them, or if it's maybe something like nursing or something where maybe there's a little more um, confidentiality issues or something with actually shadowing them. Can you offer to take the person out to lunch and interview them or chat with them about career prospects? See what a day in their life, in their job life looks like. Can you work part-time in a related field and get some ancillary experience that way? Or can you volunteer and get exposure to the field in that manner? You can see things like, for instance, the work environment that these people will typically work in. Is that something that, that you feel like you could do day in and day out? For me, I liked actuarial science, and when I was a freshman in college, I was fine with that work environment, 9 to 5, kind of suit and tie business type of environment. I realized a couple years later, though, that that wasn't really the environment that I wanted. It wasn't that, it wasn't that I did poorly on the assignment or anything, but that assignment kind of showed me what that environment looks like. And I decided, maybe that's not such a great fit for my personality. That also, when I went to Pitt, I started thinking about, well, what does the work environment on Wall Street look like? That was kind of my goal there, was go to Wall Street, work in a hedge fund. And I thought, well, I don't know if working 80 to 100 hours a week in a very stressful job, I mean, it's really interesting and fun stuff, but is that in line with my life goals? Is that the work environment I want? What are the demands on you personally? What are things like the time expectations? Um, is it kind of like a closed end job, kind of, that you clock in, you clock out, you go home and you can forget about it? Or is it like you're going to be expected to be on call and answer emails or work, evenings and weekends? Or is it, something like that? Not saying that one or the other is necessarily better, but just knowing what that expectation is. Or things like demands on your cognition or your emotional or physical health. Um, doing something like therapy. Yeah, I mean, being a therapist or being a counselor can have a really high emotional toll, right? Or doing something like in the trades might pay better, but it has a higher physical set of demands. If you're just physically wiped out, is that something at the end of the day, is that something that you're okay with? Um, Having cognitive demands is also, that's also a demand, right? We tend to not think about it so much for whatever reason, but if you're thinking hard all day long, that's just taxing. Like, you come home and you don't want to think anymore, the same way that, if you were lifting heavy stuff all day long, you don't want to come home and lift heavy stuff doing chores around the house. Same kind of thing, right? If you use up, you have an amount of cognitive resources to kind of use up over the course of a day or a week or something. And if you use a lot of that on work, you don't have as much of that to expend doing other things. So things to think about. Again, not saying that any of these is good or bad, objectively speaking, but at least having an idea of what you're kind of looking at. Uh, you might say, hey, this is exactly what I thought it was. Everything lines up. I'm going in the right path. You might say, I want to do a 180. You might say, maybe I kind of want to stay in the same ballpark, but maybe steer away from this field and towards that field. And if you talk to somebody who's doing the job you want to do, they can give you a little bit of guidance. Maybe you want to go more this direction than that direction. Well, maybe consider taking electives in this area instead of that area so much. Focus yourself a little more towards the direction that you want to go, so you can narrow your perspective a little bit. Uh, so anyway, that's the kind of thought for today. I know it's a little bit longer than some of them, but I think it is an important idea. And particularly as we're coming up on the registration cycle for spring and you're probably making decisions about what courses to take, this might be a valuable process to go through. And especially, over the holidays, you might have a little bit of extra time to squeeze in some of this stuff. And sometimes you can just shoot somebody an email or go to a job fair or something like that, right? And get an idea. And of course, always take any anecdotal things. If you know somebody, if you interview one person, that's that one person's experience. That might not be generalizable. Okay, so that is the thought for today. So finishing up section 5.3, fundamental theorem of calculus, recall that we had talked about the fundamental theorem of calculus last time. There are two parts. One is that the derivative of the integral from a to x f of t dt is f of x. And the other part is that the integral of the derivative is the evaluation of the derivative at the two endpoints, the difference of those numbers. And so this basically says something, says roughly speaking, that integration and differentiation act a bit like inverse operations of one another. So we're going to just kind of pick up where we left off. Let's look at computing a couple of integrals. So let's try to integrate x e to the x squared dx from -1 to 1. So the first thing I do is I recall that my fundamental theorem of calculus has an assumption that f is continuous on the closed interval of integration. Is x e to the x squared continuous? Yeah, it's continuous in the whole real line. No problems here. Let me try to find an antiderivative. I think my antiderivative probably is going to have an e to the x squared in it. So that when I differentiate, I still have an e to the x squared. When I differentiate, I get 2x e to the x squared. So my x e to the x squared does pop out, but I have an extra factor of 2. If I squeeze a 1/2 in there, I differentiate, the constant pops out, divides out that 2, and I get exactly little f. So fundamental theorem of calc part 2 says that I can do big F at 1 minus big F at -1. Or this is going to be 1/2 e to the 1 squared minus 1/2 e to the -1 squared is e to the 1 as well. Or I have 1/2 e to the 1 minus 1/2 e to the 1 ends up being 0. Something interesting about this, if we had looked at this and noticed the symmetry here, this is an odd function. Integrating an odd function over a symmetric interval, provided the function is integrable, is going to be 0. The antiderivative is going to be an even function, which means evaluating it at one side versus the other side of that interval. An even function means those two are going to have the same value. Subtract them, we always get 0. So we have like a mini theorem. We had a theorem that we proved carefully about derivatives of odd and even functions. Derivative of odd function is even, derivative of even function is odd. So if we integrate from -a to a, f of x dx, where f is odd, this is going to be 0, where f is odd, and assuming that that it's integrable. And integral -a to a, f of x dx, where f is even and integrable. Well, this is like integral -a to 0, f of x dx, plus integral 0 to a, f of x dx. But integral -a to 0, f of x dx, that's just going to be the same value as integral 0 to a because f is even. So it acts on the interval -a to 0 the same way as it does from 0 to a. So this is just going to be twice the integral 0 to a, f of x dx for an even function. That's not quite as easy of a result, or as nice and clean of a result as when f is odd, but still a nice, useful result sometimes. We do have to be careful. We might look at something like this and say x to the -1/3, or that's 1 over cube root of x. We might look at this and say it's odd and say that this is 0 because we're integrating an odd function over a symmetric interval. But we see we have an issue, right? F of 0 is undefined. F is not continuous. on minus 1 to 1. It's not continuous at 0. So we cannot say this. At least not yet. Again, this is an improper integral, and we'll discuss these more in Calc 2. But on the basis of the fundamental theorem of calculus, we cannot just say this is going to be 0 because we're not sure whether or not this integral even exists. Any questions so far? Okay, let's look at an example. Let's consider the so-called error function, ERF of x, which is defined as 2 over root pi times the integral 0 to x of e to the negative t squared dt. So what does e to the negative t squared dt look like? It's the, roughly speaking, the bell curve. So that's what e to the negative t squared looks like. And what does integral 0 to x, e to the negative t squared dt, give us? It gives us this area. And then we have a little 2 over root pi kind of correction constant just to make things scale properly, but this is really the important bit here. So I want to find, or sorry, not I want to find, but the error function gives me this area for a given choice of x. And I want to do two things with this. Number one, I want to show that integral from a to b of e to the negative t squared dt, that integral can be written in terms of the error function this way. And two, I want to show that the error function satisfies this differential equation, or that e to the x squared times the error function of x satisfies this differential equation. Okay, so what is integral a to b e to the negative t squared dt? Well, first I note that e to the negative t squared is continuous on the whole real line. It's integral on the whole real line. There's no problems with it. It's not like if I go outside of some nice interval, I'm going to run into problems with dividing by 0 or squirting a negative, anything like that. This is going to be perfectly fine to integrate this over any interval that we want. So I could say this is the integral from, say, a to 0, e to the negative t squared dt, plus the integral from 0 to b, e to the negative t squared dt. So this already almost looks like error function of b. And this one would look like error function of a, except that the bounds are reversed. As a side note, it doesn't matter if a and b are both positive or if a and b are both negative. We can kind of, go outside of our original interval of integration and then come back like we discussed last time, so long as everything works out nicely, which it does just fine for this function. If my bounds were reversed, if this was integral from 0 to a, this would look like error function of a, and I can reverse my bounds. And when I do that, I kind of imagine thinking all the way back to the definition of the definite integral, that dt is now being traversed the opposite direction. Instead of from a to 0, it's going from 0 to a. That's what kicks out the negative. So I can flip the bounds. That just pushes out a negative in front. And I noticed that if I multiply each of these by 2 over root pi, then I have the error function. So I have 2 over root pi, integral 0 to b, e to the negative t squared dt, minus 2 over root pi, integral 0 to a, e to the negative t squared dt. And since I multiplied each of my terms by 2 over root pi, I better multiply by the inverse, so I don't change the value, root pi over 2. Or this is root pi over 2 times error function at b minus error function at a. And as I kind of mentioned last time in a bit more of a hand-wavy way, we use this kind of idea all the time in normal distribution problems in probability and statistics in Math 165. And this is kind of the formal justification for it. Something along these lines. Now let's take a look at this function, y equals e to the x squared error function of x, and show that it satisfies this relation here. In other words, I want to compute y prime and show that I get the right-hand side out. Well, y prime is d by dx of e to the x squared times error function of x plus e to the x squared d by dx error function of x. So this first bit is going to be 2x e to the x squared error function of x plus e to the x squared, and d by dx error function of x. Let me copy that down here. D by dx of error function of x is going to be 2 over root pi. D by dx of integral 0 to x of some function is f of x, e to the minus x squared. But e to the plus x squared times e to the minus x squared, they divide out. And I have 2x, e to the x squared error function of x is y, plus 2 over root pi. Exactly what we wanted to get. So that shows that this function, e to the x squared error function of x, satisfies this differential equation. Any questions on that? Now let's look at an application. This is an application of a classification system, and this is an admittedly oversimplified version. But the same idea could be generalized. So consider a diagnostic test for, say, diabetes. I think most folks know that diabetes, at least type 2 diabetes, is when you have too high of blood glucose. Roughly speaking, that's what the disease is. So one way we can see if we think you have diabetes is we can just take a blood draw and measure the glucose. So you get a blood glucose test done, and again, oversimplified, don't run to your doctor and tell them that this is the way to do it or anything. Let's just say we do a blood draw, get a glucose number back, and we say we want to set a threshold T where if your blood glucose ends up over T, then we diagnose you as diabetic. And if it's not above T, we diagnose you as not diabetic. I guess it's not a diagnosis, but we say you're not diabetic. Now, also, for the non-diabetic population, suppose there's a blood glucose distribution function, Fn of x. So maybe we have like glucose number versus number of people or proportion of people in the population. And for the non-diabetic folks, we have some function maybe like this. Non-diabetic folks, they kind of, as a group, we're going to have a mean blood glucose that's at some point, and there's some distribution around that. Some non-diabetic folks will have a bit higher of a value, some a bit lower of a value, either just naturally or maybe because of what they ate that morning or something or whatever. I guess you should do glucose fasting, but what they ate last night. So this is the function fn. Now, of course, diabetic folks, their population is going to have a higher blood glucose. But again, there might be some overlap between the two, right? Some folks who are actually diabetic, who actually exhibit all the signs and symptoms, the risk factors, and so on of this disease, they might have a lower draw than usual. So their average draw is going to be higher for the diabetic folks than the non-diabetic folks, but there's still some variability, right? The diabetic person who is on the lower threshold of the disease and maybe who has eaten pretty healthy for the last few days versus the non-diabetic person who's maybe on the higher threshold of the not disease population and who maybe had, a couple bowls of ice cream yesterday, they might actually, cross over one another. Now I have to decide on a threshold. I can't say I want one threshold for the non-diabetic folks and another threshold for the diabetic folks. I don't know who's who, right? So I have to choose one threshold. If I choose a high threshold, like say up here, now it's like really hard in some sense to get classified as a diabetic person. That means that there's almost no non-diabetics who are above that threshold. So we almost never make the error of classifying a non-diabetic, an actual non-diabetic, as diabetic. We almost never overdiagnose. We almost never say somebody's a diabetic when they actually aren't with a high threshold. So we make that error almost never. But the problem is that there's a lot of diabetic folks that we also don't call a diabetic, right? All of these folks are their diagnosis is in error. They should be called diabetic, but our test is going to say you didn't meet the threshold. We're calling you non-diabetic. When we set a high threshold, we don't call very many non-diabetics diabetic, but we miss a lot of actual diabetics. On the other hand, if we set a really low threshold, we have the opposite problem. We, in essence, catch all of the true diabetics, essentially all of them. So almost anybody who is a diabetic surpasses the threshold, gets called a diabetic, and they get a correct diagnosis. There's very little error in that population, but almost all or not almost all, but very many of the non-diabetic folks also get classified as diabetic. So that's an error as well. We make an error here. If I pick an intermediate threshold, maybe something like here, I'm going to have some non-diabetic folks above the threshold. I'm going to call them diabetic, and that's going to be an error. I'm also going to have some diabetic folks below the threshold. I'm going to call them non-diabetic. That's an error. So what does my total error look like? Well, it looks like the error from the non-diabetics, maybe I'll draw that in blue, since the error related to the non-diabetic population, that is the integral from t, let's just say we're going from 0 to max. Let's just call this m. We might want to throw minus infinity and infinity in here, but we haven't talked about improper integrals, and I don't want to get into the nuances of that. It wouldn't really change much anyway. So the non-diabetics, we make an error for any non-diabetic who scores or whose blood glucose comes back above T. So from T to M, and the number of those people, or the percentage or whatever their population, is Fn. So integral T to M, Fn of x dx. And we also make an error when we underdiagnose the diabetic folks. That's integral 0 to t, the area to the left of t for the diabetic folks. And one approach we could take, I'm not saying this is the best approach, there are some nuances here, but one approach we could take is, I guess I broke my color coding here, that other integral should be in green, but since I've already broken it, one approach that I could take is I don't like making errors. I mean, who does want to set up a model that makes a bunch of errors? Maybe I could minimize the total error. Maybe I can minimize the sum of these two integrals. I'm going to choose t to minimize the sum. And I realize there's a trade-off, right? If I choose a smaller value of t, well, a smaller value of t makes the green area go down, but the blue area bigger, right? T small makes this go up and this go down. And if I choose a larger value of t, then this goes up and this goes down. So there's a trade-off here. It's not obvious that we can just minimize the error by pushing t way to one direction or the other. Well, this is just some function. I don't want to call it f. Let's call it g of t. If I make a certain choice for t, given certain functions fn and fd, and certain number m, if I make a certain choice for t, I get a certain amount of error. If I make a different choice for t, I get a different amount of error. I have a function of t here. I minimize this by setting g prime of t equal to 0. Let me rewrite g really quickly here. I'm going to write g of t as minus the integral from m to t fn of x dx plus integral from 0 to t fd of x dx. This way, both of my t's are at the top of the integral, and we see what we're setting up for here. I gotta scroll all the way back up here, but we're setting up to use fundamental theorem of calc part 1. I'm looking to differentiate integral from a to variable times a function dt. So what is g prime of t? What is d by d capital T g of t? It is going to be negative fn of big T plus fd of big T. When is that equal to 0? That's when we have an intersection between the two curves. We would need to know a little more about exactly the functions fd and fn to say whether maybe the minimum occurs at an endpoint, or maybe there's more than one intersection or something like that. But we're not going to take this much further than we have already. But note what we're kind of saying here is that if I move this threshold closer to the intersection, if I were to say move it a little bit left, I would pick up some extra error from the blue, but I would lose error from the green. The error from the green I would lose is the same as the error from the blue plus a bit more, right? Basically, this little almost like triangular part here gets deleted, right? And similarly, if my threshold was over here and I moved to the right, I would get rid of basically this like kind of triangular area up here. So we can see that this does make sense. That if we have an intersection and if our threshold is a little bit to the right or a little bit to the left of that intersection, if I move closer to the intersection, I'll gain some error in one direction, I'll lose some error in the other direction, but the net will be a loss. And at the intersection, that's where I should set my threshold to have the minimum total error. And like I said, I mean, it could be that these two functions intersect more than once or something, or we have a strange situation. But for kind of a nice set of functions like these that are maybe like bell curves, uh, we're going to want to set the threshold right at the one and only point of intersection if we have, say, two bell curves, two pretty nicely shaped distributions, which we would expect probably for something like this. And you might say, okay, this is kind of a silly example. When are we doing anything interesting as far as classification goes on the basis of one variable? Well, these do come up sometimes, but also if you think of maybe we have two variables, right? Maybe we say if you have a blood glucose test that's above a certain number and we do an A1C and that's above a certain number as well. Well, what have I done now? I've just, instead of one dimension where I have to set a threshold, now I just have two dimensions, blood glucose and A1C or A1C. And now I say like if your blood glucose is above a certain number and your A1C is above a certain number, then you're classified as diabetic. Now we just have a similar problem, but it's a multivariable problem. I have a two variable classification problem, or if I have three variables or more than that, then I just have a multivariable classification problem that kind of follows similar guidelines. I just end up chopping some high dimensional space into a bunch of kind of like hyper boxes. And if you fall in this box, then you're, classified as having the disease, and we can do something kind of similar. So, right, this general idea or this overall idea generalizes to higher dimensions and more complex uh, types of diagnostic criteria. But we can solve it pretty nicely and easily in the one-dimensional case. Any questions so far? Okay, next example. So back to kind of straightforward applications or examples with fundamental theorem of calc part 2. But these are integrals where the integrand is a little bit more challenging to find the antiderivative of. Integrands where it's fairly challenging, say moderately to challenging to difficult, we have tools and techniques for that, and that's some of what we'll talk about a little bit later in the next couple of classes. But we also have integrands like this where it looks complicated. It's maybe not one of um, our first kind of like uh, it's maybe not a derivative that we would have written down in our first table of functions, right? We'd write out things like the derivative of x is 1 and the derivative of x squared is 2x. And if we wrote out the first 15 or 20 of these that came to mind, we're not going to see something that looks exactly like this. But I do kind of know how lots of derivatives of lots of different types of functions work, and I can maybe make an educated guess. And I think this is something people underestimate, is that I think more often than we realize, when we have from the looks of it, challenging integral to do, and we need to find an antiderivative, we might be able to use a little more intuition than we at first appreciate. And this is especially true if we really understood well things like um, product rule, quotient rule, and especially the chain rule. So if I look at this function, the overall structure, the overall interesting thing that I see here, or maybe, looking at it as a glass half empty kind of person, the overall problem here is I have a square root, right? So having a square root like this, that it's going to be difficult. It's going to vastly narrow down the choices of functions I can start with whose derivative is also going to have a square root in it. I also note that the square root is on the bottom. Well, I know that the derivative of square root of x is like 1 over 2 root x, or basically the derivative of root x looks like 1 over root x. What's the derivative of root 1 plus x squared? I think it should look like 1 over root 1 plus x squared, more or less. This is going to be my starting place, right? It should look kind of like this. So I want to take as my educated guess, the simplest thing that when I differentiate it kind of solves the biggest problem in the integral, uh, in the thing I'm looking to find the antiderivative of. So I do see that I get that 1 over root 1 plus x squared, and that's the problematic part. Now the question is, can the rest of the details work out? Sometimes the answer is yes, sometimes the answer is no. So if I do this derivative properly, I get, well, derivative of square root of stuff is 1 over 2 root stuff times the derivative of the stuff inside. That gives me a 2x. I end up with actually exactly x over root 1 plus x squared. I think this is good practice, just building up intuition, because intuition is helpful more often than I think we realize. So this integrand is the derivative of root 1 plus x squared. So if this is little f, then big F of x, and antiderivative is root 1 plus x squared. And I need to do big F at 3 minus big F at 1. I do want to be a little bit careful here. I'm dividing by some variable stuff. I'm square rooting some variable stuff. But 1 plus x squared is always positive. Positive plus a non-negative, always positive. So the square root never has a problem. And square root of something positive is always also strictly positive. I'm never dividing by 0. I don't have any issues really anywhere, and specifically not on 1 to 3. So I can apply fundamental theorem of calc part 2, nice and continuous everywhere. So I do f of 3 is root 1 plus 3 squared minus f of 1, root 1 plus 1 squared, or that's root 10 minus 1, or not minus 1, jump the gun there, minus root 2. And that's my answer. So what about something like this? I might look at this the same as above and ask, well, do I kind of see this in my catalog of derivatives or anything that even remotely resembles this? Not really. I might be tempted to try to anti-differentiate each factor and do something like the antiderivative of the product is the product of the antiderivatives. But remember, that doesn't work. We have a product rule for differentiating that throws a monkey wrench into the mix. So we can't just like anti-differentiate 4 minus t, separately anti-differentiate t to the 1/2, and then glue the two back together. That does not work. If they were added together, that would be fine. The derivative of the sum is the sum of the derivatives, but that doesn't work for products. So I can't break this apart into products, into a product of two factors and go that route. But one thing that I mentioned was that if this was a sum instead of a product, if the overarching operation was, say, a sum or difference instead of multiplication, this would be a much easier function to find an antiderivative of. But nicely enough, I actually can do that. I can just distribute. I can make this into a function where the overall operation is just subtraction. So this is 4t to the 1/2 minus t to the 1 times t to the 1/2, t to the 2/2 plus 1/2 is t to the 3/2. Now I can anti-differentiate each term individually and then subtract the antiderivatives to get the antiderivative of the difference. So here's t to the 1/2. I add 1 to the power to get t to the 3/2. I divide by the power 3/2, or that's multiplying by 2/3. That's 8/3 when I multiply by the 4. Minus, I add 1 to the power, that's t to the 5/2, over 5/2, or times 2/5. And I was a little sloppy with my equal signs here. This is big F of t, my antiderivative. Okay. If I look at this, is there anything that can cause me trouble here? Maybe t to the 1/2, that's a square root, but I'm staying positive, so I am fine with that. I don't have any problems here. Everything is nice and continuous. I can apply fundamental theorem of calc, part 2, and get f of 4 minus f of 0, or that's going to be 8/3 times 4 to the 3/2 minus 2/5 times 4 to the 5/2, and then minus f of 0, but f of 0 is just 0, so minus 0. 4 to the 3/2, the square root of 4 is 2. 2 cubed is 8. So this is 64 over 3 minus, and then 2 to the 5th is 32, times 2 is 64 over 5, and um, whatever. I don't feel like subtracting fractions, but whatever 64 times 1/3 minus 1/5 is. What if we look at this one? We have a very similar problem to the first of these three examples. Integral 1 to 3 of x over root 1 minus x squared, and if we follow a similar strategy, I'm only off by a negative sign. I plop a negative in there. That cancels that one out. Hey, everything works perfectly. And I really want to say f of 3 minus f of 1 and be on my way. Do I have a problem here, though? I might recognize a problem if I try to plug in x equals 3. And if I plug in x equals 1, I guess I get 0. That's not too bad. But if I plug in x equals 3, I see I'm trying to square root a negative. This isn't, something's not right here. And in particular, the square root of 1 minus x squared, well, for on the interval x equals 1 to 3, that's not even the domain of this square root. So this function, this integrand, is certainly not continuous on 1 to 3. It doesn't even make much sense on 1 to 3. We can't apply fundamental theorem of calculus here. In this example, we would have realized that when we tried to plug in, say, x equals 3 into my antiderivative, we saw an example before with like the secant squared, where I think we wouldn't necessarily have realized it right away. It was a little more insidious. We had to think a little more about it to realize that something wasn't right. And there are even other examples that, we could take that secant squared example and just choose a slightly different interval where it wouldn't really be obvious at all that we had made a mistake. So we really do need to be careful to check, is it continuous? No, it's not. Can't apply fundamental theorem of calculus here. Any questions on any of this so far? Okay, on to the next section then, 5.4, indefinite integrals and the net change theorem. So definition. The indefinite integral of a function, little f, on AB is the most general antiderivative of little f on the interval that is big F of x plus c. We denote the indefinite integral using this sign. Integral f of x dx equals big F of x plus c. So a couple notes. You'll note that the indefinite integral notation looks very similar to the definite integral notation. We just don't have any upper and lower bounds. So if we write this same sign, the same symbol, with no upper and lower bounds, we're talking about the indefinite integral. If we write this symbol with upper and lower bounds, we're talking about the definite integral. Second note, say kind of analogous to the difference between, say, f prime of 1 versus f prime of x, the derivative of a function at a specific point versus the derivative of a function which is itself a new function. The definite integral acts in kind of a similar way, the definite to indefinite integral. The definite integral is a number, it's a specific area over a specific region of this function, while the indefinite integral is a new function that's related to the input function, right? I put in a function little f into this operation and I get out a function big F plus C. Versus up here, well, that's not a good one. Versus up here, I put in a function and get out a number, this number here. And note 3, we can kind of see the rationale for this notation. Fundamental theorem of calc part 2 basically says integral from a to b f of x dx is integral f of x dx evaluated from a to b. So we could rewrite fundamental theorem of calc part 2 this way. So for example, the integral of x squared dx is 1/3 x cubed plus c. That's as opposed to, say, the integral from, say, 0 to 1 of x squared dx is 1/3 times 1 cubed minus 1/3 times 0 cubed, or just 1/3. This is a number. This is a function. Or the integral of cos of x dx is sine of x plus c. Whereas, say, the integral from 0 to pi of cos of x dx, well, I suppose that's going to be 0. It's going to be a number. So this is mostly just a definition thing and a notation thing. Roughly speaking, when we're talking about the indefinite integral, we just write it as integral f of x dx. And we're talking about the definite integral, we use the similar notation, but with upper and lower bounds attached to it. Okay, and the next topic in this section, the net change theorem. And the net change theorem doesn't really say much new. In fact, we already kind of took a look at this in the fundamental theorem of calc. It really is just one of our rephrasings of the fundamental theorem of calc. Integral a to b f prime of x dx equals f of b minus f of a. So if we take a derivative, a rate of change, and accumulate it over an interval, that turns out to just be something like evaluating the function on that on the boundary of that interval. I mentioned before about how this generalizes pretty substantially, giving the name fundamental theorem of calculus some substance. So the accumulation over an interval of a rate of change gives the net change over that interval is another way to think about it. This is the net change. If we think of, say, an interval in time, if I accumulate, say, speed over time, that gives me total distance traveled or change in position. So let's look at a couple examples. The first couple will be just kind of abstract. The current in a wire is defined as the derivative of the charge. So I of t, the current at time t, equals q prime of t, the derivative of the charge at time t. What does integral a to b, what does integral a to b I of t dt represent? Well, by definition, that would be integral a to b of q prime of t dt. And as long as, q is reasonably nice, this is q at b minus q at a. It's the final charge on, say, some capacitor plate or something like that, minus the initial charge. The charge at time b minus the charge at time a. It's the net change in charge. Another example, if x is measured in meters and F is measured in newtons, maybe F is a force being applied and X is the distance over which it's applied. What are the units of integral 0 to 100 f of x dx? Maybe this is an accumulation of force being applied over these 100 meters. Well, I know that F is measured in newtons, but what is dx? If we think all the way back to the definition, we had some limit of some sum of f of xi star delta xi. We had an increment in x multiplied by a function output. Or basically, I have an increment of distance. This is meters. The unit of that is meters, multiplied by, say, a little force over that short time period, or that short distance, I should say. This is in newtons. So this dx carries the units of x. So this is meters. And this is newtons. And I'm just accumulating a bunch of newton meters. Right? So if I add up a bunch of newton meters, I still have newton meters. If I take the limit of something that's in newton meters, I still have newton meters. So I have newton meters. I have something that's like energy or work or something like that. Any questions so far? Okay, and last example in this section. Suppose that an oil tank, let's fix that. Suppose that an oil tank ruptures at time t equals 0, and oil leaks out at a rate of R of t equals 100 e to the negative t over 100 liters per minute. And our question is how much oil leaks out during the first hour. So I want to know how much leaks out. That's like oil at end minus oil at beginning, the oil left in the tank. So if I have an amount of oil at time t, this can be A of t is the oil in the tank at t. Then the rate of change of oil in the tank, that's what's given by R of t. A prime of t is R of t. If I want A at during the first hour, so that's A at 60 minus A at 0, if I want to know the amount of oil in the tank at time 60 minus the amount that was in there at time 0, that's the total amount that is leaked out. I can rewrite that as integral 0 to 60 A prime t dt. But wait, that's just integral 0 to 60 of R of t dt, or 100 e to the negative t over 100 dt. Do my units make sense? This is in liters per minute. This is in minutes, and I'm claiming that the amount that's leaked out liters per minute time minutes is liters. Is that an amount that leaked out? Is liters an amount? Yes, it is. So my units also make sense here. Good thing to check when I have the ability to use units to check my work. As much as us math folks hate units, most of the time we do have to admit they help us check our work every once in a while. So I see that an antiderivative for this, well, I have a factor of 100 that just kind of comes out. And what's, yeah. So just integrating this, I have a factor of 100 that comes out. I need to anti-differentiate e to the negative t over 100. That's going to give me e to the negative t over 100. When I differentiate this, I'm going to get a negative 1 over 100 coming down from the chain rule. So I need a negative 100 to counteract that. And I want to evaluate this from 0 to 60. So this is negative 10 to the fourth times e to the negative 60 over 100 minus e to the 0. Or this is 10 to the fourth times 1 minus e to the negative 3/5. So this is the amount of oil that leaked out in that first hour. And maybe I should, since I used units, I should actually respect them. And we will say that's in liters. Any questions on any of this? It's kind of a little side note. How much oil is in the tank, do we think? Well, oops, how did that happen? There we go. How much oil is in the tank? I mean, we have to make a couple extra assumptions here, but if this 60 were to increase to say 120 or 240 or 1,000 or something like that, what would the result be? Well, the only place that really shows up is in this exponent, right? This e to the 0 stays the same. This 1 stays the same. This factor out in front doesn't change when the amount of time changes. And as 60 increases, we get a more negative exponent. So we get like 10 to the fourth times 1 minus e to the negative, what could I call this? Like maybe little m over 100. As m goes to infinity, this bit goes to 0, and this goes to just 10 to the fourth. So, I mean, I guess if we assume that the rupture is like at the bottom of the tank, or, wherever the rupture is, the most oil that will leak out is 10 to the fourth liters. But it's leaking out really fast at the beginning and then slower as we go on. That kind of makes sense because at the beginning, there's like a large head. So it's pushing down a lot and pushing a lot of the water out. But at the end, if you've ever drained like an igloo cooler or something, like, at first it's coming out really fast, but once it gets close to the bottom, you have to like tilt it and all of that to get the water to keep coming out at a decent rate. So, so just kind of a little side note there will be 10 to the fourth or 10,000 liters that will eventually leak out. Or if the rupture is at the bottom of the drum has 10,000 liters of oil in it. Any questions on anything we talked about today? So section 5.4, not a huge section, more just kind of, it's almost like a 2.7 versus 2.8, just kind of thinking about the integral a little more generally, as we can integrate a function and get a function back, as opposed to just being able to integrate a function and get a number out. And just wrapping up section 5.3. Any questions on anything? Now that we're close to the end of the semester, things are a little more chill and we have, you know, uh, a little more time to cover each of these sections. So when we come back next week, we will talk about 5.5, the substitution rule, where we'll be investigating more challenging problems. Um, where was it? Like this one, for instance, this will be a candidate for the substitution rule. We could do it by intuition. It's kind of a challenging intuition problem, or maybe on the easier end of a substitution rule problem. I kind of would recommend working through some of the 5.3 and 5.4 material in advance of next time, because that's going to be really helpful to you want to have a bit of this intuition built up to decide what substitution to make for the substitution rule. So that is a decision that needs to be made, and having this intuition really helps a lot. So that'll wrap up chapter 5 after next time, and then we'll cover a couple of topics in chapter 6 and 7. And that's again kind of overlapping a bit into Calc 2. But we'll talk about a couple additional integration techniques, and that will be the end of the course. So it's coming along pretty quickly here. Just a little side note, when we come back from Thanksgiving break, we only have 1 week, and then we're right into finals week. So pretty quick turnaround there. So we are getting close to the end of the material, but we're also quite close to the end of the course, even though we haven't had our Thanksgiving break yet. Thanksgiving is like as late as possible this year. So just be aware that, often we have 2 weeks after Thanksgiving before the final exam, only 1 week this year. So make sure that you're ready to come back from Thanksgiving break and jump right into, final exams, final projects, and all of that. All right. That is all I have for today. So we'll end a few minutes early.